Hey guys, so today we're going to do a bit of medical physics. So medical physics is an optional topic for AQA, if you're studying AQA physics. It's also a topic that come up in OCRA, okay, just because you need to know it as well. Okay, so what we're doing today is ultrasound, okay? So we're going to go over how is ultrasound used to image inside the body, and we're going to look at then the two A scans and B scans. Again, I've done like nearly every past paper questions in 2017. So I promise what I'm teaching you in this video, you need to learn off, okay? So hopefully you find this video useful. Please watch it once through, then the second time you watch it, just pause it and make some notes, just make revision points, and then try some past paper questions. Remember, if you want to get more revision notes, you can always go to my resources where we have loads of past paper questions there for you as well and more explanations. So, ultrasound. Okay, so ultrasound, we use them, okay, and I know this sounds weird, but I didn't notice when I was way back in GCSEs. Okay, I thought ultrasound was something completely different, but it is sound waves, okay? So ultrasound, it is sound waves. So they are longitudinal waves, okay? They're longitudinal pressure waves. Remember, they're made of those compressions where they're really close together and refractions, right? The big spaces. So ultrasound are just sound waves, they're just longitudinal waves, but they're called ultrasound because they're above the range of human hearing. That's why if someone's getting an ultrasound or they're looking for maybe the baby inside the mother or the fetus is what we just call it when the baby's not born yet. So when they're looking for that fetus inside the mother, that's why you don't hear anything, right? Because they're ultrasound. They're above the range of human hearing. So what that means is they have to be above 20 kilohertz. So the range of human hearing is around 20 hertz to 20,000 hertz. So they're above the range of 20 kilohertz, right? That's why we can't hear them. They're non-ionizing, right? They're just sound waves, so they're not dangerous. It's not going to cause any harm to the mother or their baby when we're using them to look for a baby. They're non-invasive, so that just means we don't cut any holes in your body, right? And they produce images in real time. So that's why, if you've ever seen a B scan, that's the one that gives us images. We'll talk about this in a second. But that's why, if you've ever seen an ultrasound, you can kind of see like the fetus, remember it's just an unborn baby, you can kind of see it move, okay? So you get those images in real time, which is really good. However, the kind of not so great thing about ultrasound is they're not that great of resolution. So remember, resolution means to see things that are close together as separate points. So like if you ever see a B scan of the images of that baby, sometimes you can see that you can't really see like exactly where the eyes are, exactly where each finger is, because the resolution isn't as good. So resolution is the ability to see 2 points that are close together as separate points. For example, the baby's fingers, right? They're really close together, but the resolution is not that good, so I can't really see them as separate fingers. You kind of just see them as like a blurred hand, okay? So how even are these ultrasounds made? So you've probably seen again that you see that when we're taking those images of the baby. So again, the B scan I've mentioned quite a lot. That's the one that gives us the images of the baby. So you kind of see that like black and white, kind of like grainy image of roughly what the baby looks like inside there. Okay, so you've seen when people do that, what they have is they have this like probe they put over the mother's stomach. That probe is called a transducer, okay? And you've also seen that there's always this like liquid that's between the transducer and the skin. And that liquid is called a coupling gel. So we're going to talk about these now and why we need them. So, transducers. How do they emit the ultrasounds? So, what a transducer is it basically is a fairly simplified drawing. But a transducer, what it has inside it has these things called piezoelectric crystals, just like quartz. Okay, so piezoelectric crystals are inside this transducer. And in the back of the transducer, you have this thing called a backing material. Okay, you need to know about both of these things in detail. Okay, so piezoelectric crystals, they use a thing called a piezoelectric effect. And what that just means is when they vibrate, they're going to produce those sound waves, produce those pressure waves. And they vibrate because we apply an alternating potential difference. So remember, alternating potential difference just means like a changing potential difference. So what we do is we apply an alternating potential difference, a changing potential difference. And what we're going to do is we're going to apply the frequency. Remember, frequency is number of waves per second. The frequency of that alternating potential difference is going to be equal to the natural frequency of the piezoelectric crystals. So remember, everything vibrates, and they have a natural frequency they want to vibrate at. And if I apply a driving frequency at the exact same frequency that they naturally vibrate at, what we get is resonance. Okay, so you've seen resonance in other topics. And when resonance occurs, the vibrations just get much larger, a much greater amplitude. Okay, so again, piezoelectric effect. What we do is we apply our alternating potential difference. And what's going to happen is our piezoelectric crystals, or our quartz, the piezoelectric crystals are going to vibrate. Okay, they're going to expand and contract So they expand and contract, that's the vibrations. Expand and contract when that alternating PD is applied. Okay, now we know that sound waves are formed from vibrations. Same like a speaker vibrates, we get a sound wave. So because we have these vibrations, the expansion and contraction of those crystals, what we get is then we get a pressure wave. That pressure wave is the ultrasound. Okay, so the pressure wave of the ultrasound gets emitted. Okay, so there's my transistor. We just got them vibrate. The pressure wave or the ultrasound gets emitted. Okay, now I need them to stop vibrating. Okay, I need them to stop vibrating so that when this ultrasound wave, when it hits something in there, maybe it hits the baby, it's going to get reflected back. But I need to be able to pick up that reflection. So I need these to stop vibrating. Okay, so we need them to stop vibrating so they can pick up this other wave. To get them to stop vibrating, so again, I got some vibrating and I want to stop vibrating, I need to have dampening there. Okay, so we learned about dampening, we did resonance. So that's what this backing material is. The backing material there is to cause dampening. Okay, we want to dampen the oscillations, we want to stop the oscillations. So we have a backing material to stop the oscillations or to stop the vibrations. And we need it to stop so this transducer can both act as an emitter of the ultrasound and as a receiver, right? We want it to be both the emitter and the receiver. But I can only receive the ultrasound, again, if it stops vibrating. So again, we have an alternating potential difference. What's going to happen is they're going to expand and contract. We're going to emit that pressure wave. But then we're going to remove that alternating potential difference, right? And we're going to make sure that they get dampened, right? The oscillations stop, okay? The oscillations are going to stop so it can act as a receiver. So when that ultrasound wave and that pressure wave comes back, it's going to cause them to start vibrating again. So what's going to happen is the ultrasound comes back, or the pressure wave comes back, and the pressure wave is going to cause the crystals to expand and contract. In the same way that an alternating potential difference caused them to expand and contract, made a pressure wave, now a pressure wave, making them expand and contract, causes an alternating potential difference. And then that electrical signal is picked up. Okay, so what we need to do though is we need to make sure that between this transducer, between the thing that's emitting the ultrasound and receiving the ultrasound, we need to make sure we have this coupling gel between them, okay? Now the coupling gel is there because what happens is if there's no coupling gel between the transducer and the skin, there'll be some air in there, and that air is going to cause loads of reflections. And if loads of reflections happen, then barely any of them are going to go into the body, right? So I want to minimize any reflections that happen here. Okay, so that's called the acoustic impedance. So acoustic impedance basically means how much does it resist the sound waves. Okay, so if something has a high, so Z is for acoustic impedance. If someone has a high acoustic impedance, it's going to resist the transfer of those sound waves. So something like bone has a really high acoustic impedance. And it's calculated by using the density of the bone to travel the speed of the wave in that bone. Okay, so we know bone's got really high density. Okay, so the same way from the transducer to air, or between the skin and the air, so skin and air has a really large difference in acoustic impedance. Okay, so if there's a big difference, okay, so there's a big difference between the two acoustic impedances, what happens is you get loads of reflection. But I don't want reflection to happen, so that's why we put a gel there to make sure that we don't have those reflections happening. So to get the reflections not to happen, I don't want there to be a big difference in acoustic impedance. So I want to make sure that the acoustic impedance of the gel is exactly equal to the acoustic impedance of the skin. So the waves go in, okay? So we just said then, we've got the waves going in, and they're going to get reflected at these different boundaries, okay? We just said that if there is a large difference or large change in the acoustic impedance, what's going to happen is going to be lots of reflections. Okay, so because we just said bone has a really high acoustic impedance, that's why we can't use ultrasound to see your brain, because the bone has got such a high acoustic impedance, it's going to cause them, basically all the ultrasounds gets reflected, so you can't see inside the brain. Also, it's why if we're looking at someone, if their lungs are here, because the lungs are filled with air, and again, air, we just said, is a big difference in acoustic impedance between your skin or between your flesh and your air. Because a big difference in acoustic impedance, again, there's going to be loads of reflections that happen there. So we can't see anything that is behind the lungs. Okay, so again, we can't see behind the lungs, we can't see the brain, because there'll be the big differences there in acoustic impedances. Okay, next thing you know about is that there's the two types of ultrasounds. You can get an A scan, so the A just stands for amplitude. And you get a B scan, and the B scan stands for our brightness. Okay, the B scan is what you see all the time, right? When someone comes home, if they find out they're pregnant and they come home with that little image of the baby, that's a B scan, a brightness scan. So a brightness scan, what they do is, you've probably seen the movies, they move the transducer, okay, they move that probe over the stomach, okay, but remember you have that coupling gel in there, and you need to make sure that the coupling gel and transducer and the skin are always in contact, right? We don't want that any air there, so if we have air there, there'll be a big difference in acoustic impedance between the air and the skin, and we'll get too much reflection. Okay, we need to make sure the transducer is always in contact with the gel and the skin, even if we're moving it across the skin. Okay, so the person doing it has to be quite skilled. Okay, so what we do is, basically what happens is you have an X and Y axis, and what happens is your Y axis is kind of like where the location of that transducer is. And we know the location of the transducer is because basically there's like different resistances is what it uses. Okay, so all you need to know though is what it does is it uses the location, the linear location, and then how much tilt they applied. Because you have to make sure that when you're doing an image that it's basically they have to be perpendicular to each other. And if they're not perpendicular, you can't get that image. So that's why you have to rotate it around, because not everything inside your body is going to be perfectly perpendicular to that line of sight. Okay. So again, what we do is we use the X and Y because what it does, it looks at how much tilt there is, what location it is, what linear location is across the body to build up an image. Okay. And then what we do is we basically get a spot to say exactly where that transducer is. A spot to say exactly where the transducer is. A spot to say exactly where the transducer is. Okay, so again, that's how we know where the transducer is, because of whether it's the X and Y is its location or its tilt. And then the brightness of the spot is because of how much signal is received. So a brighter spot means we get loads of signal back than a dimmer spot. So that's why there's grey and black images. Where an A scan looks at the amplitude. So a B scan helps us figure out where things are, right? We get that image. Where an A scan is really good for helping us get distances. Okay, distances. But in an A scan, it can't be moved. Okay, so it has to be a perfect line between the transducer and whatever you're looking at the distance of. So one thing you might want to know the distance of is the distance of that baby's head. Okay, because the size of that baby's head lets us give information about basically how long it takes for you're going to give birth. Okay, or to see if the baby's growing well. So what happens is, let's say we start the time, right? And then the time starts, so we have our oscilloscope screen. So your oscilloscope screen is that thing that shows you the different waves. What we have is time starts, and time starts as soon as that ultrasound wave gets emitted. Okay, so the ultrasound wave gets emitted, travels. It's going to hit the baby's top of the head and gets reflected back. And when it gets reflected back, that's when we get our signal. Okay? But there's loads of ultrasound waves emitted. So again, we just said that one ultrasound gets emitted, then it hits the baby's head, comes back, gets detected. But another ultrasound, when it got emitted, it travels the whole way down to the bottom of the baby's head and then back, and then we get there. So the distance between here and here gives us information on the size of that baby's head. But remember, this signal here, the time between when it starts and when it got back, that time, remember, is double the distance between the transducer and the baby's head. Because remember, it has to go down to the head and back again. And then here, for the back of the head, again, remember, it's the double the distance, because it has to go the whole way down to the bottom of the head and then back again. So that's how we can figure out the size then or diameter of that baby's head. Okay, and just use that equation of speed as distance over time. So again, B scans are good because we can see where things are. It's really good, again, if you're trying to figure out maybe where the baby is and where the placenta is to see if it's okay to give birth. So you can't give birth if the placenta is down here, obviously. So you might need to get a C-section. So it's helped us to figure out good locations of things, where things are. Whereas the amplitude is, the A scan, the amplitude scan is good if we're trying to find out distances. So other things might be like the distances of the size of the eye, but it has to be in a perfect line then. Hopefully you found this helpful, and leave us some comments below if you did.